Hello and welcome to another video. In this video we're going to be doing chapter 1.4, which is elastic and inelastic collisions. Now, we have to differentiate between these two. So what we want to think is that in an elastic collision, all kinetic energy is conserved, or there's no loss in kinetic energy. In an inelastic collision, kinetic energy is lost. So if we thought about this as a ball hitting the floor and bouncing back up, if this ball bounced up to its original height, that means no kinetic energy has been lost. All of its energy has been converted from gravitational potential to kinetic, then from kinetic back to gravitational potential. However, if the ball rebounded and went to here, this would be inelastic because energy has been lost through friction, sound, heat. Now, when it comes to momentum, in an elastic collision, the momentum is always conserved. No matter what, it's always conserved. Always conserved. But in an inelastic collision, generally the case is two objects sticking together. So imagine two cars crashing, getting stuck together. That would be totally inelastic. Partially inelastic would be the case of the ball, where it doesn't quite reach its maximum height. With elastic collisions, total energy before will always equal after. That's how we know energy is conserved in elastic collisions. That's always the case. Inelastic, however, although momentum is conserved, kinetic energy is not. So we need to make sure we remember these distinctions. Now, let's move on to the questions. Question 1. We're told that a squash ball is released from rest above a flat surface. Describe how its energy changes if, part I, it rebounds to the same height. Now, if it's rebounding to the same height, we can establish that no energy has been lost. Therefore, the energy change can be described as elastic. Now, part 2. Describe how its energy changes if it rebounds to a lesser height. Well, this is quite simple. It's partially inelastic, because it does not stick to the floor, but it rebounds with slightly less kinetic energy. Now, let's move on to part B. In AII, the ball rebounding to a lesser height, the ball is released from a height of 1.2 meters, and it rebounds to a height of 0.9 meters. Show that 25% of its kinetic energy is lost. Now, this is quite straightforward. All we need to do with this is take our 1.2 meters, multiply it by 0.75 to find 75% of this, and this should give us 0.9, providing 25% is lost. If you type that into a calculator, you'll find it does. So there we go, we can prove that if 75% of 1.2 meters goes forward, we have 0.9. Odd question. Now, question 2. A vehicle of mass, let's do a nice diagram again, 800 kilograms, moving at a speed of 15 meters per second, collides with a vehicle of mass 1200 kilograms, moving in the same direction at a speed of 5 meters per second. The two vehicles lock together on impact. So, after the collision, we have a combined, which will be 2000 kilograms. In part A, we are asked for the velocity of the two vehicles immediately after impact. Now, in the last video, we tackled these questions. All we need to do is find the momentum of these two before, add them together, and it should equal the momentum afterwards. 15 times 800 is 12,000 plus 5 times 1200, which is 6,000. And this will be equal to 2000 V. This is 18,000. And we're going to want to divide that by 2000 to get V on its own. And that should give us 9. So V is 9 meters per second immediately after the collision. Now part B asks us to find the loss in kinetic energy. Now, if we remember our formula for kinetic energy, we know that half mass times velocity squared is our kinetic energy. So it's a very similar principle to what we did before. I might get a new sheet of paper for this. So B, what we need to do is find, in fact, I'll do this, that's better. Right. What we need to do is find the kinetic energy before, the total kinetic energy, and the total kinetic energy after. Now remember that we found V in the previous part, so V is 9. So, let's find the kinetic energy of this one. It'll be half its mass, 800, multiplied by 15 squared, plus half of 1200 times 5 squared, which will equal half 2000 multiplied by 9 squared. Now I shouldn't really use the equal sign because they may not be equal, so let's put an arrow instead. We can't always assume that it will be conserved unless it's an elastic collision, which we will find out after this calculation. So 400 multiplied by 15 squared is equal to 90,000 joules. Now we can add this to 600 times by 5 squared, which will give us 15,000 joules. And this will go to half 2,000, 1,000 multiplied by 9 squared, which is 81. which is 81,000 joules. So the total kinetic energy before is 105,000 joules, and the total kinetic energy after is 81,000 joules. So we do 105,000, take away 81,000, and this will give us our loss in kinetic energy. Which is 24 kilojoules, or 24,000 joules. That is part B. So let's move on to question 3. Now question 3 tells us an ice puck of mass 1.5 kilograms is moving at a speed of 4.2 meters per second and collides head-on with another ice puck of mass 1 kilogram, and this one is moving at 4 meters per second. After the impact, the 1.5 kilogram puck continues in the same direction at 0.8 meters per second, and the other ice puck will be the same mass, and we'll need to find V. In part A, it asks us to find V. Now, same as the last question, we find the momentum of this, add it to the momentum. We don't add in this time. In this one, we find the momentum of this, take it away from this. This is how they trick you. And this will go to 0.8 times 1.5 plus V, because there's only one of them, so just V. Now, if we do the calculation, 4.2 times 1.5, and then take away 4, we're left with 2.3 is equal to 0.8 times 1.5, which is 1.2 plus V. Now, if we take this away from this, we are left with 1.1 is equal to V. So, V is equal to 1.1 meters per second. Nice and easy. Now, part B. It asks for the loss of kinetic energy again. So with this one, we want to find the kinetic energy of this, but even though they're colliding, we want the total. So it doesn't matter that they're colliding in this case for energy. So half 1.5 times 4.2 squared plus 0.5 times 4 squared goes to 0.75 times 0.8 squared plus V. .5 V squared. Right. Sorry about losing it on the edge. Let's write that again here. V squared 0.5. Okay. So we know V now though. So that'll be 1.1. Okay, that's better. Right, so let's work this one out. 0.75 multiplied by 4.2 squared is going to be 13.23. And then we're adding that to 0.5 times 4 squared, which is 8. And this is going to 0.75 multiplied by 0.8 squared, which is 0.48. These are all joules. Plus our 0.5 times 1.1 squared, which is 0.605. Now, if we add these two together and add these two together, we will get 21.23 joules, will be going to 0.48 plus 0.605, 1.085. We take this number away from this number, we get our loss. Sorry for losing it off the screen again. If we take this number away from this number, we will get our loss in kinetic energy, which will be in this case 20.145 joules. That's how much energy we've lost. Now, last question. Question 4. The bumper cars at a fairground are designed to withstand low-speed impacts without damage. A bumper car of mass 250 kilograms, moving at a velocity of 0.9 meters per second, collides elastically with a stationary car, so 0 meters per second, of mass 200. Immediately after the collision, the 250 kilogram car is moving at 0.1 in the same direction. And this one will be moving, I would imagine, in the same direction. So we have 200, we have V, we need to find V again. So, as we have in the previous questions, 0.9 times 250 plus 0 is equal to 0.1 times 250, or 25, plus 200V. Now, this is 225. Taking away that 25 will give us 200V. This means 200 is equal to 200V. This makes V equal to 1 meter per second. Now, part 2 asks us to show that the collision was elastic. Now, to show it was elastic, we need to prove that kinetic energy was conserved. So, just to save time, I'll write down the formula and show you the final answers for these two. So that's the general idea for kinetic energy. Now, we get 112.5 joules going to 12.5 joules plus, because we know V is 1, 100 joules. Now, this is looking quite nice. So what does this tell us? Energy is the same on both sides. So, we can prove it was an elastic collision. Now, part B tells us, without further calculations, discuss the effect of the impact on the driver of each car. Now, what we can say is the driver of the car going 0.9 meters per second, when he hits the next car, his velocity goes from 0.9 to 0.1. So, the driver of car, let's call it A and B, the driver of car A will slow down, and the driver of car B will speed up. So, all we need to write is that the driver of 250 kg car slows, and the driver of 200 kg car speeds up. It's that simple. That has been chapter 1.4. I really hope it's been of help. Please like, subscribe, and thank you.